Hi, everybody. Welcome back to the Feynman Technique. So today we're going to be discussing two very powerful substitutions. They are the Weierstrass substitution and King's property. And we're going to, first we're going to use the Weierstrass substitution to solve this integral, and then show that via King's property it's also equivalent to another integral. So anyway, this is the setup for the Weierstrass substitution. So we let our t equal tangent x over 2. And you can see by this setup right here, we have our angle x over 2, and then our opposite is t, our adjacent is 1, and our hypotenuse is derived from that. And you can see that the tangent of this angle x over 2 is indeed t. And then we can see from that sine x, if we use double angle identities and everything like that, we can see that sine x is going to be 2t over 1 plus t squared, and cosine x is going to be 1 minus t squared over 1 plus t squared, and dx is 2 over 1 plus t squared. So we can use that in our integral. If we apply that substitution to our lower bound, we can see that it's going to go to 0, and our upper bound is going to go to 1. So now we plug that into our substitution, and we have this. All right, that looks awful, but that actually simplifies nicely like this. Here's all the steps, if you want to pause the video and take a look at it. More steps, and finally, we whittle it down to that, which we can split using partial fraction decomposition. Well, actually, we don't need partial fraction decomposition. We just split it. We split that into two separate integrals. This is a standard arctangent integral, and with a substitution, this turns into a natural log. Here's the steps to evaluate that first integral. It evaluates the pi over 4. We just take the antiderivative and evaluate it at the bounds. And then for the second one, we let u equal the denominator, and we have this. So now we finally have that our original integral is equal to pi over 4 minus 1/2 natural log 2. And now for our second substitution. This is called King's property, and basically it just says this. The integral from a to b of f of x dx is equal to the integral over the same interval of f of a plus b minus x. It's just symmetry. All right, and from that, if we apply that to our original integral, sine x becomes sine of pi over 2 minus x, which becomes cosine x, and the other one switches also. So plugging that back in, we can see that our sine integral is equal to this, but it's also equal to our original integral, which has the value of pi over 4 minus 1/2 natural log 2. All right, guys, I hope you enjoyed that, and we'll see you next time.